I'm Vernon Squire. I'm chairing this session, and we have two talks. The first one by Courtenay, and the second one by Elizabeth. And Elizabeth is going to be given the 2017 Rothschild Lecture, so that's quite prestigious. So we'll get on now, and this is Courtenay Strong, and the talk he's going to give, and this has changed it, is filling the polar data gap with harmonic functions. Courtenay.
Yeah, thanks, Vern. Can we dim the lights also? Or the sun? All right, so the title here is Filling the Polar Data Gap with Harmonic Functions, and this is work I've been doing with Elena, Cherkaev and Ken Golden at University of Utah. And what I have shown on the title slide here is an example of filling the polar data gap. So on the left-hand side, this is passive microwave remote sensed CS concentration from National Snow and Ice Data Center. And as you can see, there's this conspicuous hole in it where the orbit of the satellite does not allow for concentrations to be retrieved. And then here's an example of the fill, or one of the fills that I'll show you today, in the same color scale. And then there's the same fill on the right-hand side using the color scale which National Snow and Ice Data Center uses on their website. And we're grateful to National Science Foundation and Office of Naval Research for supporting this project. Here's a brief outline of what I'll present for you today. I'll first define the polar data gap, and then I'll go through some of the motivation for using harmonic functions, and in particular Laplace's equation to fill the gap. I'll present the gap fill as a Dirichlet problem, meaning that we will have a solution which matches the concentration measured by satellites around the gap. Then I'll look at the gap fill as a Cauchy problem, which means that we'll also consider the first derivative of concentration around the gap, and that will require some regularization as it's ill-posed, and then I'll close with a summary. All right, so here's the polar data gap. It's the region around the North Pole where satellite orbits do not allow sufficient coverage to estimate CS concentrations. And this gap has changed size over the record. We have a 40-year record going back to October 1978. Early in that record, the hole was quite large, exceeding 600 kilometers in radius, shown in this example from January 1985. For most of the record, the middle portion of it, the hole or gap had a radius around 300 kilometers, as shown on the right, and then just recently it's been reduced down to tens of kilometers. But most of the record looks like the example that I'll focus on here today. So NASA has been in the process of decreasing the size of that hole using satellite technology. What we'd like to think about here today is how we can fill in that hole retrospectively using mathematics. So here's an overview slide of what the model is that I'll go through with you today. We're thinking about the CS concentration field F in the region G, which is the polar data gap, as the sum of two functions. The first is a deterministic term psi, and the second is a stochastic term omega. And so this is a three-dimensional kind of relief view of the smaller data gap example from the title slide. We have higher so the vertical dimension here is concentration, and then we could think about the horizontal coordinates as, say, a polar stereographic projection of the data from the title slide. So the plateau up here on the right is higher concentrations near 1.0. That's up toward Greenland, and then as we move in this direction, we're moving toward the Russian coast. So there's the data gap shown in relief. It's the magenta circular region, and then the deterministic term we have in the middle here, we're thinking about it at this point as a solution to Laplace's equation. So it's a smooth function that captures the overall gradient from high at the upper right toward low concentrations at the lower left. And then this captures the overall gradient well, but it's missing the spatial heterogeneity present in the surrounding data. So we add a stochastic term which captures the amplitude of deviations from Laplace's equation along with their e-folding spatial autocorrelation length scales. And I'll detail how we do that in just a moment. Okay, so that's a basic overview of the fill. This raises the question of why would we start with Laplace's equation? There's a couple of motivations for that. Principally, it builds on our prior work approximating CS concentration fields using Laplace's equation, and it also is a gateway to some natural generalizations which incorporate physical processes not explicitly in Laplace's equation. So in terms of the prior work, we have a few papers now where we've thought about measuring the width of the marginalized zone using Laplace's equation. So however you define the marginalized zone, typically wave penetration distance or flow size distribution, or in this case, a concentration-based definition, such as used by the National Ice Center, you'll end up with some, in general, non-convex shape. And so how we define the width of that is made easier if we have an objective framework based on Laplace's equation. So we can solve Laplace's equation inside that non-convex marginalized zone region, and then the arc length of streamlines through that solution provide an objective measure of MIZ width. And this has several desirable mathematical properties such as uniqueness and invariance with respect to translation and rotation on the sphere, which would not be provided, say, for example, by measuring along a meridian. And as Ken mentioned, this is an example of cross-pollination where we borrowed this idea from medical imaging and the measurement of organs in various organisms' bodies. So in addition to providing a means for measuring the width of non-convex regions, Laplace's equation also is a gateway into some natural generalizations by which we can think about processes not in Laplace's equation, such as freezing and melting, time dependence, which we can diagnose because we have 40 years of daily data, advection, which we can study because we have velocity fields to go with the 40 years of daily concentrations, and potentially also local diffusivity if we consider an inversion problem. So to illustrate what I mean, I have a few equations here. This is Laplace's equation. One generalization would be to think of a source term on the right-hand side, giving us Poisson's equation, by which we might think about some sources or sinks of concentration. We could leave 0 on the right-hand side, and we could take Laplace's equation and incorporate a local diffusivity field sigma, which would allow us to represent general concentration fields as well. Once we've written it like that, it gets us thinking about diffusion type term here, which gets us thinking possibly about an advection diffusion type equation for concentration, where we could either have or not have the sources. The point is that Laplace's equation is just a beginning. CS doesn't obey Laplace's equation per se, but this is a framework upon which we can try to understand how, why, and when it deviates from Laplace's equation, and then we can pursue mathematical frameworks for investigating that. Okay, so back to the framework, or back to the model we're proposing here. The deterministic function psi, as I mentioned, is assumed to be a solution to Laplace's equation, and at first we'll think about this as a Dirichlet problem, meaning we'll have psi solving Laplace's equation on the polar data gap, which is shown in a diagram here as region G. This polar data gap has radius r1. I'll use r and phi throughout to indicate the radial and angular polar coordinates centered on the pole. And so as the Dirichlet problem, psi solves Laplace's equation for every point in G, and then we have the boundary condition given by concentration on the outer boundary, the function G. And we know a unique solution exists if the boundary is sufficiently smooth and this function G is continuous. So I'll give you an example of what Laplace's equation looks like in the polar data gap once again. It's the same example I showed you before from 30 August 2007, but here I'll add the map so we can see this in a larger perspective. So on the map, obviously this is Greenland up here, this is Russian coast here, and the polar data gap is this circular region indicated by the magenta circle, and that's where we don't have the data. So if we take that same concentration field and show it in relief in the middle panel, where the vertical dimension represents concentration, we see the higher concentrations close to Greenland at the upper right, transitioning to the lower concentrations closer to the Russian coast at the lower left. And the solution to Laplace's equation looks like this. This is obtained numerically by finite difference, and we see that that captures nicely the transition from high concentration to low concentration. There are some issues with it, in particular the first derivative, which I'll come back to, but at first start, it gives us at least the large-scale concentration gradient. In addition to having some issues with the first derivative around the boundary, it's also missing the texture or spatial heterogeneity characteristic of the data around the gap, which brings us to the stochastic term. So the stochastic term omega is modeled as spatially correlated zero mean additive Gaussian noise, written like this. So omega depends on the radial and angular coordinates r and phi, and it has two parameters, sigma and eta. Sigma is the standard deviation of the amplitude, and here by amplitude we mean the deviation of the concentration field from Laplace's equation. How large is that in the positive and negative direction? And we diagnosed that from observations for each day of the year, and I'll show you that data in just a moment. The parameter eta is the spatial correlation e-folding scale. So if I calculate the correlation between concentration, deviations at one location and deviations at another location, at what characteristic spatial scale does that decay to 1 over e? And then we have a convolution here, which is done in a computationally efficient manner via fast Fourier transform, which is what the F denotes. And the convolution is of two functions, a capital gamma, which has the parameter sigma in it. That's spatially uncorrelated Gaussian noise. And then we have the lowercase gamma, which is a two-dimensional Gaussian with standard deviation 2 eta. And so via this convolution, we obtain a amplitude and spatial autocorrelation length scale, which are consistent with the statistical properties of the noise sampled around the data gap and applied on top of the gap. And so that, yep.
The observations you have, where are those located? From which you're getting sigma?
So this is, yeah. I'm going to show that actually on the next slide. Thanks, Chris. So this is that same example. So here's the polar data gap, which is the area where we don't have data with a green circle around it. And then to answer Chris's question, it's a good lead into it. This is where we measured the CS concentration random function. So to investigate these parameters sigma and eta, we took samples of the stochastic process. So for each of these regions, M1, M2, M3, we took a sample on each day of the year of the stochastic function. So that sample is defined as the observed concentration field minus the solution to Laplace's equation inside that circle. And because we know the actual concentration, differencing them gives us a look at or sample of this stochastic function. And so we do that for each of the regions, M sub j for j1, 2, 3, for each of the days of the year. And what we found through this analysis was that the parameter eta, which is the e-folding length scale of the spatial correlation, was reasonably constant throughout the year, but the parameter sigma varied markedly. So the amplitude of the deviations from Laplace's equation changed rapidly and markedly moving into the melt season. So when concentrations are high early in the calendar year, this parameter sigma, diagnosed spatially inside each of these regions, had a value around 0.01 and then increased to 0.05 moving into the melt season. So it's important to capture that temporal variation in the amplitude of the stochastic noise, and we did that with a Fourier expansion or Fourier series. And so using the mean and only two terms from the Fourier expansion, nk equals 2 accounted for about half the variance in sigma, and that's this blue curve here. So after we solve Laplace's equation in each gap, we then generate a stochastic realization of the noise function with sigma varying as shown here, and add that to Laplace's equation. And here's what that looks like. Again, the same 30 August 2007 example. There's the gap, and then here's the deterministic function once again, and this is the deterministic plus stochastic term on the right-hand side. So we've seen that several times. Let me show it to you in a different perspective now, which is on a map view, as we had it on the title slide. So there's the 30 August 2007 example. On the left-hand side, here is the polar data gap filled as we've modeled it here using the ubiquitous MATLAB jet color scheme. And then here's on the right-hand side the same solution, but shown now with the National Snow and Ice Data Center, maybe more physically realistic color scheme. And let me show you another example. This is from 6 January 1985. This is that larger polar data gap that we had early in the record. This gap is larger than 600 kilometers. I think it's 611 in radius. So here's the gap fill in the MATLAB jet color scheme, and once again in the NSIDC color scheme. And these are examples that Ken and I presented in remote sensing and also in a recent SIAM newsletter. And then I want to show you another perspective, which is an animation. So this is running from May 2007, and it will run through the end of the calendar year 2007. So you'll be able to see the ice go through a melt process. And so the fill is in the middle here around the North Pole. It's about that large. I didn't highlight it with a magenta circle so that you have a chance to assess visually the degree to which this fill captures the large-scale gradient and also produces realistic spatial heterogeneity consistent with the data around the gap. So I'll just let that run through the end of December. There we go. Okay. Up to this point in the talk, we've thought about using the concentrations around the gap, but we have a lot more information. The next natural place to go is to think about what the first derivative of concentration looks like, because the sea ice likely follows that coming into the gap. All right, there's not likely to be a sudden discontinuity in the first derivative. So it's natural to also investigate the degree to which we can approach this as a so-called Cauchy problem. So Cauchy problem means that we're going to consider the concentration around the boundary in addition to the first derivative. So let's add a little bit more information to our schematic. The polar data gap is still the region G, and it has an outer boundary G sub 1. And let's add an inner boundary G sub naught, and we still have a radius on this gap R1. So now with the Cauchy problem, we want psi to solve Laplace's equation for every point in G. We still want the Dirichlet boundary condition, where concentration on the outer boundary is given by the function G, which the solution satisfies. But we'll add the new Neumann boundary condition here now, where the first derivative of concentration in the direction normal to the outer boundary, which is the n vector, which would of course just be the radial direction for a circle, but more generally it's in the normal direction, is given by some function h for all points in the outer edge. Now first of all, most of you know that the Cauchy problem for Laplace's equation has a compatibility issue. So there needs to be a compatibility for a solution to exist. There needs to be compatibility between the concentration and first derivative boundary conditions. So that's one thing we need to keep in mind. In general, we're not going to have that as we go into actual observations. Moreover, the Cauchy problem for Laplace's equation is well known to be highly ill-posed. And so we will need some kind of regularization procedure to obtain a solution in this case. And as our regularization strategy, we chose to work with a constrained minimization shown here. So we're trying to minimize the function given on the first line, which is the sum of two terms subject to a constraint. So the function we're trying to minimize, the first term here, is the L2 norm on the outer boundary of the difference between our solution and the observed concentrations. The second term is a weighting factor beta times the L2 norm again on the outer boundary of the difference between our solution's first derivative and the boundary condition first derivative. So we're trying to minimize that, and we want to minimize it subject to the L2 norm of the solution on the inner boundary not being larger than alpha. And the reason we pick that particular constraint is clear from the general form of the solution to Laplace's equation in polar coordinates. One way we can write it, and I'll call this regularized solution psi sub r to remind us that it arises from regularization, can be written as the sum of complex coefficients a sub k and b sub k multiplied by radial basis functions. And these radial basis functions, e to the I k phi, have coefficients in front of them. In the first term, it's r to the k, which is fine. In the second term, it's r to the minus k. And we need to be careful of that term r to the minus k because it's trying to get very large as we get close to the center. So a lot of the papers that have looked at Cauchy problem for Laplace's equation use a relatively narrow annulus so that the inner radius might be 70% of the total radius. Here, we really want to try to get as close to the pole as we can, so we need to watch that second term. Okay, so let me show you what happens when we numerically investigate this as a Cauchy problem. So once again, at the upper left, we have the solution to Laplace's equation, which is this smooth deterministic function. This is not the regularized version, it's the one I showed you before, right? That nicely captures the large-scale gradient, but it appears to have some unrealistic changes in the slope of the function or its first derivative, particularly up here at the upper right. If we think about this as a three-dimensional topographic surface, those are concentrations in dark red very close to 1, so that would be a flat plateau. And then suddenly when we cross the boundary of the gap, that function transitions down with a discontinuity in the first derivative to the smooth solution to Laplace's equation. Not entirely realistic. So what do we do about it? Well, we pose it as a Cauchy problem. And so now we have the regularized solution, psi sub r. It's got this singularity near the pole I'll come to in a minute, but I just want to emphasize what's nice about it is around the perimeter, we're matching very well now the first derivative of concentration and the concentration itself. In particular, coming off this, what I'd like to think about as a flat plateau of concentrations near 1.0, we continue that flatness of concentration, at least for some distance inside the gap. So what's happening around the perimeter now looks very nice. In fact, nicer than the solution to Laplace's equation alone. But of course, we have the solution approaching positive and negative infinity as r to the minus k, from the r to the minus k term as we're getting closer and closer to the pole. So bring in our regularization, make alpha smaller, right? So the constraint that we imposed was that we want the norm of L2 norm of the solution near the pole not to be larger than alpha. So if we just make a smaller alpha, we can minimize that positive and negative infinity type behavior around the pole. However, as a compromise, we're starting to lose the fidelity of our boundary conditions. In particular, notice that the nice continuity of that flat plane of 1.0 concentrations at the upper right has now been replaced by something which looks like a compromise between these first two solutions, right? So here we come across flat, and then it's not as severe as the Dirichlet problem on the left-hand side, but we still see some discontinuity in the derivative. So what are we to do? Well, we have some kind of compromise in front of us. We can either stick with just the solution we had, or we can try to incorporate some of the properties of this second solution, in particular the fidelity of the boundary conditions, by combining them in some way. Maybe a linear combination that changes its weighting as a function of r, or more elegantly, we can just go into the solution itself and introduce a new weighting term here. If we introduce that weighting term, which I'll explain in a second here, then we can obtain a solution which looks like this at the lower right. This is kind of the best of both of these solutions, right? Toward the middle, it has the smoothness and non-explosive behavior of the solution to the Dirichlet problem, so we avoid the singularity. And as we get toward the outside edge of the gap, we transition to something which looks more like the middle solution, the regularized solution. So we can have a reasonable solution at the pole and also results which match the concentration in its first derivative on the outer boundary. And we accomplish that through this weighting function. So what is this weighting function? Well, it's just a coefficient in front of the term which is going to get large close to the pole, right? So it's the weighting function. It depends on r, and it's sitting in front of r to the minus k. With that weighting function added in, we denote the solution by psi sub r star. And what is the weighting function? Well, there's several that we could use. The one we're looking at now is an arctangent type weighting function. So we have the radial coordinate r on the x-axis here. On the left-hand side, r equals 0 is the pole, and on the right-hand side, r equals r1 is the outer boundary of G. And this function transitions in a sigmoidal fashion from 0 to 1, so that right near the pole, we get 0 influence from the second term. As we move out to the outer edge, we get the full influence of the second term. What's nice about that is it eliminates the singularity at the pole, and it also provides us with the original full solution right at the boundary, meaning that we match the Dirichlet and Neumann boundary conditions. So this is a relatively new idea in our group. We're looking at different ways of doing this, and we have yet to reprocess the entire 40-year satellite record using a solution like this. We've already done it and published it for Laplace's equation alone. But from the test cases we've looked at, this explains generally more variance than Laplace's equation alone, which is evident just by looking at it and thinking, how realistic is that? How much variance in the overlying CS concentration function would that explain if we look at it in test regions around the pole? Okay, so in summary, a partial differential equation based model with tuned stochastic spatial heterogeneity provides an efficacious fill for the polar data gap. And what do we mean by efficacious? We mean that this solution accounts for more than 50% of the variance in the observed concentration field in test regions around the gap. And of course, that explained variance comes entirely from the deterministic term, as the stochastic term is uncorrelated with the observations. We start with Laplace's equation to build on our prior work and to provide a gateway or foundation for physically motivated extensions which account for processes not explicitly in Laplace's equation, like diffusivity, source terms, advection, etc. And we can get at the form of those by looking at the difference between the true ice field and Laplace's equation. And we have natural generalizations of Laplace's equation, such as Poisson's equation, and incorporation of a local diffusivity. that allow us to try to investigate the physical meaning of these deviations from Laplace's equation. And then finally, we found with appropriate regularization that the solution can satisfy Cauchy boundary conditions, meaning the gap fill matches concentration and its first derivative on the boundary. Thank you very much.
Are there any questions?
Sorry, this sounds like a painfully obvious question. How do you know it's any good? Or let me phrase it another way. So you could either use an artificially large data hole and then test your model against the real data inside that artificial data hole. Or you could believe that client models work and client models and CI models don't have data holes. So you could see how well this infill works against those models.
Yeah, this is a good suggestion. So on the first point about making the data hole bigger, one disadvantage to that would be that we would be looking at a narrow annulus again, which is actually easier to solve because we don't have the singularity at the pole. But it's a good complementary analysis, right? At this point, we chose to look at filled circles around the data gap. Disadvantage of that is we're assuming that the properties of the ice in those fills is the same as the properties of ice in the gap. I like the idea also of looking at a model output, right? And I also like the idea further of actually filling the gap using a model, right? And because we're looking at a very simple kind of like low order mathematically based framework for this, but you could take it, right? You start with just filling it with a constant, the most naive possible, right? Then you have a plane, then you have Laplace's equation, and then way over here you have a, like have a CIS model. And so I'm interested in that full range of possible fills and also comparing to what you have from a thermodynamic and dynamically based model. Thanks.
You've probably tried this, but have you tried an intelligent filter, a sort of Kalman filter approach? Where you
So kind of like a data assimilation framework
Yeah.
where you'd like run a model and incorporate available observations.
so that
Yeah, that's a great idea, especially because of the emerging things like ice bridge and available data for like limited transects to the pole. Yeah, and I guess I also didn't answer Danny's first question, which is how do I know it's any good? So just
I'll let that slide because
because the answer is I don't know. No, actually we do know. So again, the way we do it is we assume that the concentrations observed around the data gap are representative of what's in the gap, and so then we go to the gap. We go to those sample regions where we know the actual concentration function, and we look at, for example, the correlation or bias statistics, the skill of the fill in those regions where we actually know the answer. And so as I mentioned, I call it efficacious because we explain half the variance with Laplace's equation alone.
There's another question there from Gray.
Yeah, can I modify Danny's question a little bit? Rather than asking, is it any good? Is it good for what? In other words, what do you want to do with this infilled data once you've got it?
Thank you for asking that question, and now I can't believe I didn't put that on my motivation slide. So it's a great question. So why would we want to do this? Well, first of all, as a climate scientist, I'm interested in long-term change and decadal variability. So if you look back at the beginning of the record and you have a 600-kilometer gap, maybe it's okay to make the assumption that that's ice-filled early in the record. But now we have lower concentrations making their way up into the gap, so we need some objective way that we can agree on making a long-term trend and extent without assuming it's filled. That's one reason. Another would be, say, model initialization. So if you want to initialize a sea ice model, and I think after we published this, that was most of the emails I received from people wanting the data were trying to initialize the model. They wanted an objective fill for that region rather than just arbitrarily assuming it's 1.0 concentration. So those would be just a couple of the motivations. Thanks.
Okay, well, thank you.
Okay.